Now that we are ready to go into the next level of our code review process, which will be more geared towards Kubernetes deployments, let's just have a quick recap of where we stand right now. So from an application development process, we have containerized each of the component so that it is now a container image, and these images have been pushed into the Docker Hub repository. At this point, I would again highly recommend that you take a look at the architecture that we discussed in one of the previous videos. These terms are something that we will now refer to as we look inside our code and try to deploy these components on the Kubernetes cluster. So before we jump directly into the code, let's first square off some of the logistics around the Kubernetes cluster. Because this is a local development running on my MacBook, we will be using the Kubernetes that is installed along with the Docker for desktop. So please make sure that this is enabled. You could also use other standalone Kubernetes clusters like Minikube, but just for the purpose of this example and consistency, I would recommend turn on the Kubernetes inside the Docker for desktop. Now there are two paths to access the cluster information. One is from the command prompt, and the other one is by installing a Kubernetes dashboard on your machine. The documentation for the Kubernetes dashboard is available online. Let's first take a look at how do we use the basic Kubernetes commands on the command prompt. This is not an in-depth Kubernetes course, so we will keep it to high-level utilities that we will be using in our exercises. So the first and foremost command that we run is the kubectl get all. This lists all the resources that are currently running on our Kubernetes cluster. So as you can see, there are some pods, there are some services, the deployments that control these pods and services, and have also created some replica sets. If we try to look at the similar information from the Kubernetes dashboard, we find a similar information from the Kubernetes dashboard as well, which in my opinion is comparatively easier. So we got the deployments, the pods, replica sets, etc. Now there are some other components as well which we are going to use in our project, like the config maps, the secrets, ingress, etc. But we will come to them as we walk through these exercises. Let's take a look at the database component and how it is deployed in our Kubernetes cluster. Our database component comprises of multiple Kubernetes objects such as deployments, secrets, persistent volumes, volume claims, and services. Each of these objects define the state of our application in the Kubernetes cluster. The pod and the pod template is provided in the deployment. The deployment also uses secrets to hide entities such as username and password from being written in clear text. The physical volume in which the data is stored is managed through persistent volume object, and means to access that physical volume inside the pod is provided through persistent volume claims. Lastly, the replicas of the pods are load balanced using the service object. Let's start with each of these objects and dive a little deeper in them. Let's start with deployments. The deployment ensures the state of the entire application. The YAML describing the deployment is spread into multiple parts, and we will go through each of them one by one. The first piece is the spec. Spec defines the number of replicas for the pod that will be contained in them in this deployment. In this case, we are saying there is one replica. And how the replica is going to be identified? It's going to be identified based on a matching label. So any pod, when it has a label, Kubernetes will go and find all the pods that match the label as specified in the match label section, which in this case is app:/MongoDB. It is a key value pair, and you can freely choose any key and value. The next section is defining the template of your pod. This is where, if you see, the label is app:/MongoDB. So this means that the pod definition contains the label which is matched with the deployment label, and that's how the deployment knows which pod it has control over. The next section in the template, which is still under the template definition of the pod, is defining where the volumes of the storage for this particular pod is going to come from. We are saying here that the pod volume is going to be based on a persistent volume claim, and the name of the claim is Mongo-PVC. So let's now take a look at where the storage come from.
Storage comes from the persistent volume claim, which is yet defined as another object. You see the name of the metadata is Mongo PVC, which matches with the volume specified in our deployment template. The specification for the volume claim are that it is a storage class of a manual, has a read-write access, and approximately requires 1 gigabyte of storage space. This persistent volume claim looks up to the persistent volume, and here we see some detailed specifications of the actual volume that are accessible to the whole Kubernetes cluster. Here we see some similar attributes such as the storage class name, the read-write access mode, and the storage size. But then in addition, it also tells you where the storage is coming from in terms of the physical storage. And that in our case is being specified as /tmp/mongopv. So if you tie back this chain once again, the persistent volume is created as a separate object, which is then referenced inside the persistent volume claim, and this claim is being specified inside the pod template. Moving on to the next section. The next section contains the containers. Now, what the pod is comprised of? The pod is comprised of multiple containers. In this case, the container that we are going to be using has a name Mongo, but the image is actually coming from the Docker Hub or a container repository, which in this case is Mongo latest. Now we go here further and specify some other attributes of this container, such as what the container port is. That is, when the container is initialized, the port that it will be listening on is 27017. Now, this container needs the actual volume mount points. So this is where we will specify a volume mount point and specify that inside the container, you want a mount path of /data/db. This still has nothing to do with the persistent volume that we specified earlier. This just means that we are going to see a path called /data/db once this container is initialized inside the pod. The last section here is specifying the environment variables on that container. So because this is a standard Mongo image provided from Docker Hub, it specifies that once the database is initialized at the start, it needs a specification of a DB username and a DB password. So what we have done here is we create an environment variable according to the specifications named Mongo _initdb _root _username. And the value for that is basically a DB username. Same goes for the initdb root password. Now, however, because this is a sensitive piece of information, you want it to be encrypted in some form. So Kubernetes allows this kind of sensitive data management through an object called secret. So that's where secret comes into play. Now let's look at the secret configuration. So the secret here contains a data element which further contains key value pairs. And the key in this case is a DB user with an encrypted username and a DB password with an encrypted password. These are base64 encrypted values. The same DB user and the DB password are referenced into the environment variables where it specifies the name of the environment variable, and right below it, it specifies the value is going to come from a secret key reference. The name of the secret key reference is secret, and the key to be used is the DB username. Similarly for the password. Finally, once the pod definitions and the replicas are created, the next thing is service. The service is specified based on the selector. So the service is a very simple definition that has a specification section that specifies the selector is going to be the key value pair of app MongoDB, and therefore it refers to the deployment. But then the service also specifies something else, which is the ports. The port from which this service is going to be accessed on, a TCP port 27017, and the port that it maps to on the other side of the service, which is inside the pod or inside the pod container, is 27017. So now that we understand the Kubernetes objects, let's go ahead and deploy them. But before we deploy them, let's quickly check the status of our Kubernetes cluster, and we're going to use the Kubernetes dashboard for that. As you can see, the Kubernetes dashboard at this point contains some standard services and some standard objects, but does not contain any object of our application deployed right now. Going back into the Visual Studio Code, you know that by now that all our Kubernetes code is maintained in the K8s directory, the database specifically in the DB, and there are some common configurations such as the secret, config, and ingress in the commons directory. We will also then come to the middleware and the front end in just a bit. So let's first get some common elements out of the way, because we know those are the foundational elements that some of the further Kubernetes objects are going to rely on. At least we know the secret is the most important one right now. So let's go ahead and deploy it. The command to deploy the Kubernetes objects is kubectl apply, and you can specify the YAML file that specifies that object. It's a -f. Let's just first get the secret deployed. The secret has been created, and now the key value pairs that the deployment for the MongoDB is going to need are available. Let's still go ahead and create the volumes for our MongoDB. So the command for that is kubectl apply -f commands, and we are going to specify the Mongo volume. So as you can see, the persistent volume and the volume claim have also been created. Let's quickly go and validate what our Kubernetes cluster is showing right now. So the Kubernetes cluster has got the secret that we specified, and if you look inside the secret, we can see that our DB password and DB user is available as a data element. We also have the persistent volume being shown here. Let's now go ahead and deploy the actual database. So kubectl apply -f DB Mongo YAML is now going to start deploying the MongoDB deployment and the MongoDB service. So let's go back into the dashboard and see what's happening. The dashboard now contains the MongoDB deployment, which created a MongoDB pod based on the replica set that we had defined. So as you can see, we had specified one replica set which contains one pod. Because we have now created the MongoDB, let's go ahead and also install Mongo Express, which is a Node.js application for accessing the MongoDB. So in order to deploy that, it is the same set of commands, kubectl apply -f, k8s, db, and Mongo Express. So the Mongo Express gets deployed again as a deployment and as a service, as you can see here. So going back into our Kubernetes dashboard, we see that the Mongo Express is being started, which also then created a Mongo Express pod and a replica set for the same. We also see the services that are associated with each of those deployments, and they have got an internal cluster IP. As specified in our architecture discussion, the Mongo Express service is a load balancer type of a service, and therefore it creates an external endpoint on port 8081. So if we click here, our Mongo Express front end opens up, and here we can now take a look at the MongoDB that we just installed in our previous step. So the MongoDB and this unique ID ending with VM5WH is the pod that this MongoDB Express is addressing, and it is addressing because we specified the MongoDB service, which is then load balancing it and pointing the requests to the only pod for the MongoDB. So at this point we can administer our MongoDB, we can create databases, we can create collections, etc. But we will skip that for now. So moving on to the next components of our application is the middleware. So let's take each middleware component and quickly look at the deployment specification here. The deployment for the order component is the deployment contains again one replica which matches the labels based on app order, which is also specified in the template for the pod that will be used. The pod contains a container, and in this container, we have specified the name of our image for our orders app, which was written in Node.js. So why don't we first verify whether the Docker image exists? So at this point, we see that it only has the Mongo and the Mongo Express, but we do not see the order container image downloaded yet. So you don't have to go ahead and download it manually. Let's just go ahead and finish with the deployment of the order component. So let me just clear off the screen, and the command we're going to run is kubectl apply -f order deployment YAML. So the deployment has initiated deployment of the order and the service. And as you can see here, the deployment for the order is complete. It has created a pod based on the replica set and then a service for order service. To validate the point we made earlier that the Docker image was pulled from the Docker Hub, let's look at the Docker images once again on our local repository and here is the Docker image that Kubernetes pulled for us. So that's how Kubernetes allows you to deploy your application on any Kubernetes cluster as long as it has a connection to the repository of the Docker images that is being used in that deployment. Lastly, from a middleware standpoint, let's continue deploying our product component. And if we go back and look into the Kubernetes dashboard, you can see that the product deployment is also complete along with its product service. The last component we are now going to be deploying is the front end. And the front end also contains the deployment with the image for the web app that we created earlier and then the service. So this is also very similar to the previous step. So let's check again, and the web app service and the nodes are being created. So the web app deployment consisted of two pods as we had specified for the web app replica set. So at this point, our entire application is up and running and is all available with internal cluster IPs. Our application is still not ready to be accessed externally. So what we're going to do here is, if we need to implement our ingress, we are going to be implementing two ingress endpoints here, one for the APIs and the other one for the web. So let's go ahead and deploy the ingress components. So as the ingress components are deployed, we can go ahead in our dashboard and check two ingress components. When ingress components are deployed, an external endpoint is also made available, as we saw in our architecture. If you access the web component, you can see that the application is up and running. We also see that an endpoint for API is created, which we know according to the definition of the ingress, it consists of two paths, one for product and one for orders. So now that our application is running and all the components are deployed, we had created a functionality to load some standard products and allow us to create orders. So once that the data is now inserted through the REST API, and let's go ahead and place an order. So with this quick verification, we should be able to see that our app is up and running fine. We could also go inside our Mongo Express to see that the database was created, which now contains products and then also contains the order that we just placed. So that completes the deployment of our full stack, which includes the database, the middleware, and the front end, which we also accessed through our browsers and verified that everything seems to be running fine.